Okay, for the shear wall thickness, we will discuss it because from the previous discussion, we only have the PMM or the flexure checking in the DCR, demand capacity ratio of the longitudinal bar. So that is given to us by the display design info, the DCR here. We just check the flexural design. So this one. So in our discussion, because of the DCR or the pure DC, I am referring to DC ratio. So DCR, when I say DCR, that is demand capacity ratio. Okay, the DCR is above 1, that is 1.2 for this pair. So that's why it will give you filled in PMM interaction or flexure. So what to do as per the discussion, you have to add the rebar or increase the capacity. How to increase the capacity? You can increase the thickness or the length. Okay, so to have or increase the concrete prime of C or the strength to have the value less than 1. So that is for the flexure only. Flexure and PMM. Okay? PMM axial and plane induction out of plane moment. Then this checking already has a checking for shear capacity or how to define the thickness of the wall. So I have the capacity, but the thickness of requirements is, I don't know if it's adequate or not. So because here it will just give you a warning, and from here it will also give you the flexural design and the shear design. So from the shear design, you have here a also PU, MU, VU. So we are dealing with this one. So this is the VU. This is the VU, if you can see this one. So this is the VU. The VU is the shear force, ultimate shear force acting on that pier to this pier, or either left or right, or this is the quantity, 3,732. Okay, then you have a VU. Then to determine the thickness, we have here, just like for the shear, so this is a shear wall. If you notice, or if you remember the shear, how to deal with the shear for the beam. So it will just, for the beam, let's say this is the beam, you have a reaction. Of course, you have a VU, so you have a reaction, you have a load here. Let's say I'm talking to the beam, so it will crack like sometimes like this. Yes, this will become the crack failure. So same for the shear wall, it will crack like that. So what is the capacity of the section? So the capacity of the section is BC plus BS. So this is for the concrete and for the steel, but this will equivalent to BN. Okay, so this is equivalent to VN. So we are talking to this VN, but if you write the equation for the BN is equals VU, this BN, VBN will give you VU. So the P factor, this P factor or the reduction factor will be multiplied to BC plus BS. Okay, so for the code provision of the wall, let's say we have here, I have here code provision. I put it already in this Excel. Thickness of wall requirements. So I have here a determining the concrete shear capacity. So I have a code. This is ACI 318M-410. This is also same to NECP 2015. Okay? So, the shear force is limited to maximum of Bmax. ACI 11.5.4.3. So, from the ACI 318M, 318-14M, okay, we have here wall, chapter 11, from this, 11.5, so this is the 11.5, 11.5.4.3, this is the code. So, there is a written in the code, this is in plane shear, okay? So, we're dealing with the in plane shear. If I'm in the plan, this is your shear, this is your VO, so that this is the in plane. So, the out of plane is here, okay? So, this is your plane along this axis. So, this is the in plane shear. So, the VN at any horizontal section shall not exceed 0.83 square root of F prime of C HD. So, there is a provision for the thickness. So, you will find this equation, Vn equals Vc plus Pbs. But your Vn shall not exceed. So, I will make it bigger. So, you have value of Vn. You have value of Vn. This is your Vn. You have a prime of C. You have H. You have D. So, your H is thickness of wall, and D shall be taken as equal to 0.8 LW. So, for the in plane shear, the design H, shear design H is the thickness of wall. So, you have thickness of wall, and D shall be taken 0.8 LW. That LW is the total length of the wall. So, if this is your H, thickness of wall, and this is your LW, I mean, this is your D, this is 0.8 of LW. Okay? So, you have LW, 0.8 LW, that is equivalent to your, that is the value to use to find Bn. Okay? So, you will now have this value. Let's say, we have Vn. So, our Vn is equals 0.83 times square root of, let's say we have 7,000. So, 7 times 6.9, it will give you megapascal, times 600 times 0.8 times 3 meter or 3,000. So, it will give you Vn. So, convert to kilonewton, divide mo ng 1,000. MPa, Newton per mm squared, this mm squared, so Newton. So, divided by 1,000, it will give you kilonewton. Okay. So, but you have VU. You have VU here. So you have VU. Your VU is equivalent to for this load combo, you have this VU 3732. Then you have PBC, you have PBN. I don't know why this value is the same. PBN. Maybe what happened to this? Okay. But we will go back to our, so we will select this VU 3732, or you can find it here from the let's say I will just click this one, then display, show table, pair forces, then I will just select the ultimate envelope, then I will be getting this value 3167. So I have this value VU 3167. So but the okay, so I have VN and I have VU. So this is the comparison. So if you're in this case, the VU is less than VN. So our thickness is okay. Okay, so this is the one checking for the thickness of the shear wall. Okay, so I also have here, this excerpt is from pure design of the ATABs. This is how the ATABs formulate or program. Okay, then this is how the ATABs program. So else if VU less greater than Vmax, so this is the Vmax of the code, this one, or that is equivalent to this one. Okay, so if VU greater than Vmax, so you have to increase the thickness of the wall, or you have to increase the strength, concrete strength. Okay, so this is the discussion for the shear wall thickness.